Okay, so today we're going to combine what we did with the... Oh, still not up there. Okay, still screen. Today we're going to combine what we did with the projection operator with the molecular orbital diagram. And so we're going to start with a pretty complicated molecular orbital diagram, the one for ethene. It's actually out there on the wall. So you can go out after this class and go look at the poster-sized version of what we just did today, and you can see it. If you want a copy of that, I will post for everybody the PDF that has the full-size thing, and then you can, if you want to pay the people that tries to print it for you, you can put it in your bedroom or whatever you want. And then this 3 foot by 4 foot MO diagram for ethene. Okay, and so it'll be fun. Yeah, or not. But anyway, I love it. I got ragged on because I had a periodic table in my kitchen, you know, and my roommates were just like, oh, come on. So let's just dive in. So today we're going to draw the MO diagram for ethene. The skills we use today are going to be the same skills you're going to use on the homework that you're doing for hydrogen peroxide. So I picked hydrogen peroxide because it's an interesting little molecule. It's C2H. It has a mirror plane. It has a C2 axis, and that's about it, right? Has a inversion, yes. So it has a E, which everything has E. It has a C2. It has an inversion and a mirror plane. So you only have 4 columns. And so if you're going to go do the projection operator and everything by hand, I gave you a pretty easy one, a character table that only has 4 columns. And y'all did the projection operator for the last homework, and the next homework you're going to then create symmetry adapted linear combinations of the molecular orbitals on the hydrogens and the oxygens. And so how many is that? Well, each oxygen has 4 valence. You only do the valence orbitals. So the 2s, the 2p's, there's 3 2p's on each. So that's 2 oxygens, so that's 4. That's 8 orbitals there, and then the 2 hydrogens, 9, 10. So you have 10 atomic orbitals that you'll mix together, and you'll mix them in pairs. You'll mix the 2 hydrogen orbitals together, and you'll mix the 8 oxygen orbitals together, because those will be the symmetry adapted linear combinations of the chemically equivalent atoms. And then you'll take those and mix them to make the molecular orbitals. So we're going to do the same thing for ethene. We have the 2 middle carbon atoms and then the 4 hydrogen atoms, and we're going to treat the 4 hydrogen atoms together because they have the same electron cloud, they have the same 1s orbitals, the same nuclear charge. They're the same in that structure. So they will behave the same. Those electrons can't help but oscillate with each other because the forces are the same. Okay. And then the same with the carbons. The 2s orbitals are going to interact with each other because they have the same forces, and the same with the p orbitals. So let's dive in and we'll look at ethene. Here's the character table. Here's the structure and the coordinate system. Now, I will confess that ethene can be confusing in terms of its coordinate system, right? Because it's a D2H molecule. So it has a principal symmetry axis that's a C2, and then it has 2 perpendicular C2s. So which one is the principal symmetry axis? Do you see the question? It's a difficult question. If it was a D3H, I'd have a C3 and I'd have 3 C2s. And so the C3 is the principal symmetry axis. That's important because the principal symmetry axis is the Z axis. But in this molecule, it's hard to know, right? And so I had to analyze this character table to see what they were using as the Z-axis. And so I'm giving that to you. You might have made a mistake there and put the Z-axis along the carbon axis or between the carbons, where, you know, like if your Z-axis was where I have my X-axis, then what would happen is just your B1, 2, and 3 would have just switched, and you would have labeled one of the orbitals B3, G, and I would have labeled it B2G. So we would have just switched the identities of a couple of the orbitals, and that would have been the only ramification. Okay, so it wouldn't have totally broken the problem, but we would have had different answers. And so I'm giving you this coordinate system because this way you'll be able to follow through all of these. So for C2, for ethene, the coordinate system, there is a little bit of a trick there. And so I had to just look to see what they were describing in terms of the Z-axis with this character table. For your molecule, hydrogen peroxide, it's not a problem because you only have one axis, the C2 axis, and that's coming out of the plane of the molecule, and so that's your Z axis. And so when you're talking about then the PZ orbitals on oxygen, they go along that axis. The PX orbitals, PY orbitals, they're going to match those other axes. Okay? All right. So with this, we've got two types of atoms in this molecule. We have the carbon atoms and we have all 4 hydrogen atoms. So let's just grab the hydrogen atoms and let's do the projection operator to see how those 1s orbitals will talk to each other, right? Well, they'll either be in phase or out of phase, and there's different ways they'll be out of phase. So let's go through. Here's our character table, our projection operator. We have, we're going to project this AG symmetry through this molecule and through the character table. And so we have the E operation operating on the 1s orbital on hydrogen atom 3. So we're going to start with this one, okay? And it's an E. So I do an E on the molecule, and that orbital stays on H3, okay? And it has a +1, which I'll just keep as an open circle, okay? So I'll just put a little key here that plus equals open and minus equals shaded. How's that? Okay? All right. So if we do a C2 around the Z-axis, and remember our coordinate system, the Z-axis is coming out of the plane, then that hydrogen 1s orbital on H3 goes over to H6, and we see that here. You see the H6, and so it puts it over here on this one. And it's a plus, therefore it's an open circle. It's not shaded. Do you remember the projection operator? We go through every one of the operations, and then we see what happens, whether it changes sign or not. If we have a C2 around the y-axis, so that y-axis, it's going to the other side, so then it comes over here to the H5, and we have a plus sign. And then if we rotate it around the x-axis, that's rotating it down. This y on the x, this y is rotating it that way, and then the z-axis is rotating it around to the other side. Okay, it goes over to H4. So we have an H4. It's a plus here, so it's an open circle. And so that makes sense, right? This A1 or this AG combination is that fully symmetric combination where all the 1s's are expanding together and contracting together. They're all the same sign. If we did the inversion, we get confirmation. We invert it over here to H6. It's still a plus. We did the reflection in the XY plane. That's the plane of the board, so it stays put on H3, and it's a plus. The XZ is the plane of this horizontal plane, so it goes down to the H4. It's still a plus. And if we did a YZ reflection, it goes over to H5, and it's still a plus. So simplifying this, I have for the H3, I have a plus here and here. H6, I have a plus here and here. H5 is plus and plus. H4 is plus and plus. So I have this combination as the AG combination of my 4 hydrogen orbitals. Does that make sense? And that's always going to be one of the options, is all 4 the same color. And you might come up with that and say, well, I know all 4 are going to be the same color on one of these atomic orbitals, but which row is it? The projection operator tells us which row produces that image. Okay, and that's the AG row.
Is the hydrogen you chose for each operator, is that arbitrary?
As long as you label them and then you keep the same scheme through the whole table, yeah, it's arbitrary, but as long as you don't change it up, it'll work.
Okay.
Yeah, so pick a scheme, so pick a scheme and then stick with it through the whole table and you're good.
Okay.
Like I could have labeled the hydrogens 1, 2, 3, and 4. This just was the atom labels that came out of Gaussian. So when I calculated this molecule in Gaussian to actually get the pictures of the MOs, this is what came about.
Oh, so just to, I guess, clarify the question. So like on the E operator, you chose H3. Could you have chosen H4 there?
The E operator. Oh, yeah, I could have started with H4 here, and so then all of these labels would have changed accordingly. Yeah. So like if I had relabeled this, like if I'd have started down here with 4, then when I did the C2, it would get H5, and so under the C2 instead of H6 it would be H5, and under the Y rotation it would be H6 and instead of H5, and then this rotation instead of H4 would be H3.
Okay.
And so we just swap the labels on all of those places, but we would still end up with the plus, 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 plus.
Yeah. Okay. I see what you're saying.
Yeah. Now we get into the interesting ones, the B, 1G, and further ones where we have some minus signs in here. So I didn't bring down the 1S's and so on. I just really focused on the minus signs, because notice how if I start with an H3 on all of these, this is going to be H3 all the way down, right? And if I do the C2 rotation around Z, that H3 is always going to be the H6. And so this is going to be H6 all the way down. So I don't need to write that over and over again. The only thing that's changing is the plus or minus sign, whether it's shaded or not. Okay, so let's start here with the B1G. I start out with the H3 atom. I do an E operation on it. It's still open because it's a +1. But now when I rotate it around the C2, it becomes H6. Okay, and it's a +1. You see this plus? On this row, we're doing the second row. So we had a plus for the E, a plus for the H6 on under the C2 around the Z. Then I do a C2 around the Y, and I move over to H5, but it's a minus sign. Therefore, this is shaded. And so we're going to have some nodes now. And then I do the rotation around X, and I go down to H4 here, and I have a minus sign there. Therefore, this one is shaded. And so this second row has produced this pattern for the first half of the character table. Let's continue on. So for inversion, I invert H3 and it becomes H6. So it comes over here and it's still a plus sign. So that matches. So I'm going to put a check mark by this, okay, because it matches what I had on the first half of the table. XY reflection, it stays on H3, and that's a check mark. It's the same color. Do this XZ reflection, and it goes to H4, and I have a negative sign, and that's already shaded, so that's a check mark. And then H5, after YZ reflection, it moves over there, and it's a minus sign, and it's already shaded, so that's a check mark. So all of this picture is confirmed by the second half of the table. Okay, so we have this second combination that is B1G. Okay. So we've got, of our 4 hydrogen 1s orbitals, we found 2 symmetry adapted linear combinations. So we're going to have 4 total. Even though this table has 8 rows, only 4 of them are going to be non-zero. So let's look at one that cancels out. So B2G. So we do the E on H3. It's unshaded, plus 1. The H6 is shaded, though. Because of this negative sign here. So I'll draw a little arrow down. It's going to be really confusing with all these arrows, but we'll deal with it. Then the rotation around Y, H5, I have a plus sign, so it's unshaded. And then H4, rotation around X, this is shaded. Now that looks like a legitimate orbital, right, with a node down the middle. But let's go to the second half of the table. This inversion says H6 should be open. And H6 is not. Okay, so that's not confirmed. So I'm going to put an X there. See, it cancels. I have a minus H6 and a plus H6. So when I sum this row, the H6s are canceled. So that one is gone. When I do the H3, this says H3 should be shaded, and it's not, so that's canceled. Okay. The H4 says it should be plus, and it's a minus, so that one's canceled. And the H5 should be a minus, and it's a plus, so that one's canceled. So all 4 orbitals are canceled out, so we end up with a 0. So when you go through the whole table, there is no symmetry combination of these 4 H atoms that is a B2G orbital.
So all those rows that end up equaling 0, would those be the atomic orbitals of the carbons?
They don't have to be anything.
Okay.
Yeah, they don't. Yeah, we're just using the character table to project these orbitals through and see which ones survive, and the ones that don't survive are of no consequence.
Okay.
Yeah, so it's nice. Now let's look B2U. I think I can just probably go through now. This is again H3, H6, H5, H4. So these headings don't change. We just need to look at the pluses and minuses. So for the B2U, we have a plus on H3, so that's an open circle. We have a minus on H6, so that's a shade. Throw some shade on that H6. We have an H5, okay, that's shaded. And then a positive H4, so that's open. Okay, now let's check with the second half of the table on this B2U row. H6 should be shaded, and it is. H3 should be shaded, open, and it is. H4 should be, looks.
It's be shaded on the first half as well.
H6 should be shaded, and it's minus, correct. H3 should be open, and it is. H4. Oh, did I screw this up?
Yeah.
I did. Okay, let me back up a little. I got a little ahead of myself. I must have drawn the circles on the wrong things. So let me go back. Okay, so H3 should be open. So we do that. Okay, H6 should be shaded. So we'll do that. I was all impressed with my joke. That's what, H5 should be open. That's what I screwed up right there. And then H4 should be shaded. And then we check our work. H6 is shaded, and it is. H3 should be open, and it is. H4 should be shaded, and it is. H5 should be open, and it is. Okay, so that one survives, and we have that B2U combination. And it has a node down the middle here. Yeah. And then what do you think is left? The B3U, right? It's going to be the node that goes this way, right? And this one has 2 nodes. The B1G has a node down the middle here and a node down the middle here. So we found one node. This one has 2 nodes. This one's going to have 1 node going this way. But let's just confirm. So H3 is open. H6 is shaded. Okay, then H5 is shaded. And H4 is open. So there's our node in the middle. Let's confirm. H6 should be shaded, and it is. H3 should be open, and it is. H4 should be open, and it is. And H5 should be shaded, and it is. And so those are the 4 symmetry-adapted linear combinations of the atomic orbitals on H4. So I just, in case the pictures were ugly, I went ahead and included them here in nice little circles. And then this is what Gaussian gives. So I took the optimized, just sort of how to get these pictures of just the 4 hydrogens. I took a Gaussian computation of the structure of ethene and optimized it, and it finished. And then I went into that structure and I deleted the 2 carbon atoms, okay, and left the hydrogens where they were. And then I did not optimize that. I just ran the energy calculation. And the energy calculation calculated the wave functions, the 4 hydrogen 1s orbitals in those positions. And there they are. So those are the actual Gaussian versions of these symmetry-adapted linear combinations. And you can see here, all 4 of these 1s orbitals have merged together, okay, to form this blob of electron density that the electrons are spread around all 4 nuclei. And then this is the B3U. You can see they're labeled here. And so Gaussian says this one obviously is the lowest energy, the AG, because no nodes. So you should be able to rank these in terms of their energies. Now, whether you decide which one of these is higher energy or not is going to be some debate, right? Because they both just have one node, but this one has two nodes, so it's clearly higher in energy. So the B1G is up here, the B2U is here, the B3U is here, and the AG is there.
But the B2U and B3U would not be together.
Then another thing too is when you put electrons in those, they typically will split. Okay, and so yeah, you might put them in as degenerate. That would be a legitimate option, that you would put them in side by side. Okay. Okay, so I'm trying to think, what else can I say about this? Also, this would be the hydrogen side of a molecular orbital diagram. So you know how you have a molecular orbital diagram for a diatomic? You have the two atoms on either side, and then in the middle you have the diatomic and you have the molecular orbitals. Okay? We're going to be making a similar molecular orbital diagram, but one side is the hydrogens and the other side are the carbons. Okay? So it's still got two sides, but each side is no longer a single atom. One side is the symmetry adapted linear combinations of the hydrogens, and the other side is the two carbons. Same on your molecule for hydrogen peroxide. One side will be the two hydrogen atoms because they're equivalent, and the other side will be the two oxygen atoms. And then you'll combine those symmetry adapted linear combinations to make the molecular orbital diagram.
Could you work sort of backwards? You draw this out, because I can visual the four hydrogens and shade them and make all the different patterns.
Yeah.
And can I work backwards to get my AG and my...
You can, like we did with the last two lectures, was if I start with these combinations, and think about it, it only makes sense, right? If I've got this with no nodes, I could draw a node across the middle, and I could guess this one, right? And I could draw a node across this way, and I could guess that one, and then I could draw the two nodes and guess that one. So you can come up with these four pictures with your brain. You don't have to use the projection operator. And then you go to the character table and you say, if I rotate this this particular orbital around this axis, I get a -1 because they change color. But if I rotate around this axis, I get a +1 because they don't change color. And so then you could work your way through the character table, sort of using a projection operator backwards, and get the particular rows. And this one, if I invert it, I equals -1, right? Because I've changed color. Whereas if I invert this one, I equals +1, right? And so you can know if they're G or U, and you can pick your rows, and you can do it that way for sure. Okay. Now, are y'all ready for the carbons? We're going to do the carbons in the middle, and those have s orbitals and p orbitals. Okay, so let's just do the s orbitals first. Now, I changed the titles up here to kind of make each slide a little more clear. So look up at the top. Yours doesn't say 2s, but go ahead and put a 2s up there on this page. You see that in the title? It doesn't say 2s, whereas my title says 2s.
Yes, between the south and the atom.
Yeah. So this is the 2s orbitals on carbon. So we're just combining the 2s, and you'll do the same thing for your oxygens. They can either be in phase or out of phase, right? And so this is one of the options, and this is the other option. Those 2s orbitals. It's so simple, right? There's two atoms, two orbitals that are s. They're either in the same color or not.
Slow down, teach.
What? Okay. All right.
I don't want you going too fast.
Okay. Just let off the accelerator. Yeah. And so this is again, if you then operate on this one all through the character table, if you rotate around the z-axis, the y-axis, the x-axis, if you invert it, if you reflect it in all those ways, this one is going to be +1 in all of those because they're the same color. And so this is going to be that top one. The AG, so this is the AG symmetry. And then if we just took this one through and we have that coordinate system with Z coming out here, X, Y, I can't draw straight on this tablet. And you do the rotation, so we rotate around Z, we get a -1, and so we know it's either this one, this one, this one, or this one. If we rotate around X, we get a +1. So rotating around X over here, it could be that one, right? I'm filtering now, and it could be that one, Okay, do you see that? I've got a -1 there, a +1 there. If I rotate around y, I'm going to get a -1. And so here's rotating around y. It could be that one. It could be that one. Okay. Now let's do some inversions. I invert this. I just pick an arbitrary point on that, and I go through the center of mass to the other side. I get a -1. And so then it's got to be this one. So it's just after those four, I've narrowed it down to this row. I can go ahead and finish out and reflect through the XY plane, which is the plane of the paper. So I get a +1. If I reflect in the XZ plane, which is this plane here, I get a +1. And if I reflect in the YZ plane, swaps them, I get a -1. So again, once you make your pictures, you can compare them to the character table and you can arrive at the symmetry. So I end up unambiguously confirming that this is the B3U combination. Questions on that before we add in a p orbital, because the p orbitals are a little more complicated. You'll do this for the oxygen and you're going to get pretty much the same results but a different character table. You only have 4 rows. Okay, so it'll be much easier. Okay, so we can do the PZ orbitals. These are the ones that come in and out of the plane. So they can be out of phase or they can be in phase. Make sense? PZ orbitals, they're coming in and out of the paper, and so they're either coming in and out together, which we call that a pi bond, or they're out of phase with each other, we would call that a pi star. So if we take this B1U here, let's do B1U first. Well, I don't know, B2G. Let's do B2G. So one of the things I like to do first is the inversion operator. So looking at this orbital, the center of mass is right there in the middle of the molecule. What is the character under inversion? Don't cheat. Don't look at the G.
It should be...
it should be +1 if it's a G, right? So I just told you not to cheat. But if we go through the center mass to the other side, we see the same color. So that's a +1. So we know we're in the top half of the character table. Okay? And now pick a column. What do you want to do next?
GPZ, or the CY, the C2Y.
C2Y. Okay, so we're rotating around the y-axis. And so the y-axis comes out of this molecule. We're rotating around this way. And so we're rotating C2, right? 180 degrees. So this red goes into the red. The green goes into the green. We should be a +1. So C2Y gives us a +1. And that's here, and that's here. Okay. And so let's pick something that will discriminate against the first row and the third row.
Reflection and XY.
Reflection and XY. So right here, we're going to look at reflection and XY. So that's the plane of the paper. So if I reflect this PZ orbital in the plane of the paper, the red reflects into the green and vice versa. So that's a -1. So XY should be -1. So it should be this one. And so we've confirmed that it's plus under inversion. It's got this one here and that one there. So we've confirmed that it's got to be this row, because there's no other row that contains all of those things. And then we can confirm with all of the other motions, but that tells us this is B2G. So that's a faster way to combine your things. I just like to show the projection operator to show all the rows that happen to equal 0. Okay. The XZ plane, so that's the horizontal plane. It's going to be a +1 because this is the red reflecting from the top into the bottom. Reflection in the YZ plane, that's left and right, and so that's this red reflecting into the green, and so that'd be a -1, so that's confirmed. Rotating around the x-axis, that's this x-axis right here. So that's this green rotating into this red. And so that's going to be a -1 around the x-axis. Rotating around the z-axis, that's going to be rotating around this axis that comes out the top. And so this red would rotate into this green. So that'd be a -1. So we've confirmed all of the ones for that particular orbital. It's B2G. Let's take this other pattern here in B1U. we could just confirm that, inversion here is going to be a -1. So it's a U. Pick another column. XY reflection. So XY reflection is the plane of the paper. And so this red's reflecting into the green. So that's a -1 on reflection in XY. So it's either this one, this one. So we check it's in -1 under inversion. It's got to be one of those two for reflection. Let's pick the next reflection, XZ. Okay, so that's this plane here. So the top of those orbitals reflecting into the bottom of those orbitals, so that'd be a +1. And so it's going to be that one. And so we've already arrived at that particular row. We could do this YZ reflection. So left and right, it's also plus. Rotation around X, that's going to swap them. If we rotate around the X-axis, this red rotates into the green. So that's a -1. If we rotate around Y, then this red rotates back into that green back there. And that's a -1. Rotating around the Z-axis is this rotation here, where this red rotates into red and green rotates into green. So that's a +1. See how easy it is? Once you get the picture, you can go backwards and kind of work your way through the character table. You could also look at this particular pattern and see that that is oscillating in the Z direction. And so this would have the same symmetry as Z. And if you look at the character table, you'll see that Z is on that row. So that's even faster. Yeah. Same with this one back here. Let's see. Where's my mouse? This one right here, this is, again, this has the symmetry of X because it's along the X-axis, and this row has X on it. Yeah. Okay, now let's look at these two. They're in the plane of the paper. This opens up a little bit more confusion in terms of changes from your past, right? Does this look like a pi bond? It looks like a pi bond, doesn't it?
Yeah.
Okay. It's side-on interaction. And so our labels of sigma and pi are hard labels of sigma, pi, sigma star, and pi star. Remember last time I kind of blew your mind about saying local bond theory was garbage? Okay. Okay. The hard designations of sigma and pi only apply to diatomics. Or like isolated pi bonds, right? I mean, like, think of benzene. Are there 3 pi bonds in benzene?
No.
No. You know that. You're comfortable with that. Okay? We draw the Lewis dot structure. We put three pi bonds, right?
I don't do that anymore. It's too simple.
Yeah. But like this one here, we've got 1 pi bond in ethene. But yeah, we've got a lot of side-on interactions in the sigma plane. In the sigma framework, we have a lot of side-on interactions. Okay? But don't get confused. This is not a pi bond or a pi antibond. Okay, this is in the sigma framework of all of the sigma bonds between the carbon hydrogens and so on. And so the PZ orbitals are the pi bond that we just did. There's no hydrogens interacting with this orbitals here. Okay, so it's not in that carbon hydrogen carbon carbon bonding network except for the pi bonding between the carbon atoms. So this was what you would call a pure pi bond. Okay.
In both of those, there's a node in the plane of the board.
Yeah. So it's not interacting with the hydrogens at all. Yeah.
So the hydrogens rest on the node.
Yeah. And so this one, even though it's side-on interaction, it's really interacting with those hydrogens, and the carbons are interacting with each other. But you got to sort of back away from your idea of this concept of every bond has 2 electrons associated with it, and those 2 electrons are located between the atoms. That's local bond theory. This is molecular orbital theory. Okay. So again, walking through, and we're going to run out of time if we go through every one of these. But you now know the skills of going through the periodic, or going through the character table, and looking at, inversion. So this inversion, this is a -1. This one is a +1 under inversion. Makes sense, so you can do all of this for these orbitals, but I don't want to run out of time. And that puts us on the B2U row for this one, the B1G row for that one. Okay. And then the 2px orbitals. These are kind of interesting. This looks like that sigma bond between the carbon atoms. This is very familiar to you from like diatomic MO diagrams. And so when they're out of phase, they're kind of squished because you can't overlap them if they're out of phase. And so we have these particular setups. Again, this is inversion. If I pick this spot arbitrarily, go through the center of mass to the other side of the molecule, it's the same sign. Whereas this one, so that's why it's a U, okay? And then you do the other operations and you end up with B3U and AG for these particular orbitals. So what we've done for carbon is the same exact answers you would get from any other diatomic. You would have the side-on interactions, you have the 2s interactions, and so on. And so when we plot these, they look a lot like a diatomic molecular orbital diagram. So these are the symmetry-adapted linear combinations for C2. So we have the two s orbitals. Here and here, they're in phase and out of phase. That's the AG and B3U. And then we have all of the p orbitals interacting. This is the PZ orbital here interacting, and this is the PZ orbital interacting. So this is really what we would call that pi bond and that pi star bond. And then these others are all taking place in the sigma frame with the hydrogens, but we don't have the hydrogens yet. We're going to do that next. So this is the left side of our MO diagram, and the hydrogens will be the right side of our MO diagram, and then we'll mix them all to make the molecular orbitals. Okay. So let's just walk through. This top was the 2s orbitals, and so they gave us those two. This was the 2pz orbitals here. These are the 2py orbitals, and then the 2pz x orbitals that are actually in the line with the two carbon atoms. Do y'all have the arrows on yours?
No.
No? Okay. I'll go slower if you want. Here's the 2p, here's the 2s orbitals. Can you see those?
And so the top one versus the bottom one?
Yeah. And again, we're looking at the bottom has 0 nodes, and then we have 3 orbitals with 1 node each, and then we have a couple of 3 orbitals with 2 nodes each, and then the top one has 3 nodes. So then the 2pz orbitals, they form that traditional pi and pi star interaction. Okay. All right, and then we do the 2py orbitals. So those are in the plane of the paper, going up and down. Okay, and then the last ones are the 2px orbitals. Those are the carbon that end on interaction, like the sigma interaction of those 2p orbitals. In phase and out of phase. In phase where there's that little green ball in the middle, and out of phase where there's a node separating the two. And my pictures that I drew just with circles, in PowerPoint, were not that bad compared to what Gaussian gave. You see the pictures, they do look very similar. Gaussian's a little bit more relaxed in terms of what it lets the electrons do. I just did spheres or circles. My arrows essentially do what I did with this ink here. Okay. Any questions about this so far? And it makes sense, right? If I bring two carbon atoms together in a molecule, that their interaction is going to look like a MO diagram for a diatomic because it's a C2 in the middle surrounded by 4 hydrogens. Okay, now how do we mix these all together? Okay, this is the key. All the ones that have the same symmetry are the ones that mix. And so let's bring it all together. On the left, we have the carbon orbitals. Now, there's some white spots because I've blanked out. It's real busy. It's a very busy molecular orbital diagram. Okay, so I've blanked out some of them. Right now, all I'm showing are the AG orbitals. So I have 2 AG carbon symmetry adapted linear combinations, and I have 2 AG hydrogen ones. And so those are only ones that are going to interact with a non-zero interaction because they have the same symmetry.
So we're going to make 4 lines in the middle to make up those.
Yeah, so we're going to bring those together and make 4 energy levels. Bring in 4 symmetry adapted linear combinations, I get 4 molecular orbitals. And you're going to do this with your hydrogen peroxide. So you're going to have some A1 or whatever the A's are interactions, and those are the only 2 you have to mix together. And they come together and form, however many numbers you have, and the lowest number of nodes will it be at the bottom, and the highest number of nodes will be at the top. Make sense? Yeah. So I have this one here with this hydrogen with no nodes, and here on the 2 carbons with the 2s orbitals with no nodes. They mix together and make this one beautiful low energy blob of electron cloud. And that's pretty obvious, right? This AG mixes with that AG to produce this one. That's the easiest one. And that's always going to be your lowest energy one with no nodes. And so you'll have the 2s's on the oxygens for your hydrogen peroxide, and you'll have the fully symmetric combination of hydrogens which are in phase, and they'll all be the same color, and that's going to be your lowest molecular orbital. Now, how do we know it's the lowest energy? It has no nodes, which means no curvature or low curvature, which is low kinetic energy. And it's got the largest box. So with the largest space to move around in, it's going to have the lowest energy. Yeah. So then we mix them in. So when I have this one here, remember that, look how these hydrogens are kind of got a little thin spot in the middle. You could mix that in with this one that has a green, 2 nodes here, a green spot in the middle, and make this orbital. Do you see how that the 4 hydrogens are still in phase with each other? And that green spot on the 2px is still green, and that's mixing these A1 AG orbitals together to form that one. See that picture? It's okay. And then up here, again, the hydrogens are still the same shade. They just happen to be green. And this is a little hard to see, but the carbons on the outside of those carbons is red, and the middle, that green goes between the carbons. So there's still a little green in between the carbons. So this is just this particular orbital out of phase with this one, and that's where you get those nodes. Kind of hard to understand. Maybe if I drew it like this, I would have hydrogen. Oh, sorry. Let me draw hydrogen. I'm going to shade that, leave this middle piece open, and I'm going to shade that. And then my hydrogens are open. Do you see that little hand drawn? That would be acceptable for that particular orbital. I just take this picture here, and I put the hydrogens, and all 4 hydrogens have to be the same shading. Okay. And I see several nodes. I see some vertical nodes here. I see some horizontal nodes there. So I could count up 1, 2, 3, 4, like 4 nodes in there. Okay, so those are the AG orbitals. Now let's mix in the B3Us. So look at which ones show up. On the left, we have 2 more. Okay, so look on the left. I'm going to turn it on the carbon. We have 2 more on the left. And on the right, the hydrogen, we just have 1. So we're coming in with 3 new symmetry-adapted linear combinations, 1 from the hydrogen and 2 from the carbon. And so that's going to produce 3 more energy levels in molecular orbitals. So which ones showed up? The B3U. Notice right here is a B3U. Right there. And then coming up here, there's a B3U. There. and there's a B3U way at the top. So those three came in, and again, the hydrogens are opposite side, left and right are different, and so left and right are different here. That naturally fits really well with the two P's on the carbons being out of phase with each other. So this red 2P is just enveloped the two hydrogens that were red, and this green 2P enveloped the two hydrogens that were green. So that one's really easy. And you'll have the same thing with your oxygens. You'll have the 2P on the oxygens out of phase, and they'll match with the two hydrogens that are out of phase. And you'll just draw a circle around both and shade one of them. Up here, they could be out of phase. And so again, the hydrogens are green while the carbon is red, and these hydrogens are red while that carbon is green. Okay. And then this one, these 2px orbitals, you're going to have hydrogens on the outer side of that. And so those hydrogens can be red on the green side and green on the red side, and you end up with this particular picture. So that's the three molecular orbitals that come from the B3U combination. Then we have the B2U. So let me oscillate this. I've got 2 on the carbon coming in. See the B2Us on the carbon? And I've got 1 on the hydrogen side. So we come in with 3 new symmetry adapted combinations. We get 3 new molecular orbitals. And so let's find out where those show up. These are B2Us. And so here's the B2U. Okay. Here's the B2U on the right. Okay. And where's the other one? Oh, I just come in with, let's see. No, I just come in with 2. 1 on the hydrogen, 1 on the carbon. And so I make 2 molecular orbitals. Yeah. So when these 2 hydrogens are the same and these p orbital on the oxygens are the same color, then I get this one. When they're out of phase with each other, I get this complicated picture. Okay. This one, it would be acceptable if you drew this. See if I had these shaded like this. Let's see, B2U. Yeah, shaded like this. And then I had the hydrogens out of phase. So this one is open and this one is shaded. Make sense? Okay, and so that's what that's this picture right here. You can do that. It's just p orbitals and s orbitals. And you just pay attention to the shading based upon your symmetry adapted linear combinations. Okay, and then we have the B1G. So let me oscillate this. The B1G, we have 1 on the carbon showing up and 1 on the hydrogen showing up. So this one on the carbon and this one on the hydrogen, and that's easy to combine, right? You just bring those down to this one here, where again you've got that pattern of the x times y, and then up here this one up here, the B1G up here. It's that same pattern, but now the hydrogens and the p orbitals on py orbitals are out of phase. So that's a little difficult to draw, but you could do it. You have the p orbitals out of phase. And it's out of phase with the hydrogens. Make sense? Yeah, so either in phase or out of phase, same shading or not. It's that simple. And you already know the symmetry because you're combining ones of same symmetry. So you know that these are B1G orbitals. And then lastly, the pi bond, okay? This is the PZ, HOMO and LUMO. So the PZ orbitals here just come across because there's no PZ. There's no B1U, or let's see, yeah, B1U symmetry adapted combination on the 1s. So this is why this is a pure pi bond. It doesn't interact with the hydrogens at all because there's no symmetry of a hydrogen that is a B1U. So this B1U here comes straight across, and that happens to be the highest occupied molecular orbital. And then this Did it turn out to be B2G? Yeah, the B2G. This should be B2G. So there's a mistake there. Change that to B2G. And so that's the pi antibonding orbital. Now, spectroscopically, is this a colored substance? Well, this arrow, I went ahead and looked at the energies. That arrow is the visible spectrum. So visible light will get us this high in this molecular orbital system. So this tells us that this molecule is transparent in the visible region, because there's no energy level in this range here that could absorb visible light. So that's pretty cool. Yeah. So not only that, can you get the electron energy diagram, you can look at it and compare those energies and say, where would this absorb? What color would it be? You know, those kinds of things. And next time we're going to get into the selection rules with the transition dipole moment integral. Is this even an allowed transition? Can I get an electron to go from the B1U orbital to the B2G orbital? And so that's what we'll do next. But this was a big steep climb today. Hopefully you followed me, okay? If not, we've got the video and we got the poster out there where you can really look in close to these different orbitals. And if you want to, you can download the poster. So this is available. All right, we'll see you next time. I'm glad we made it through. So that was a lot of work.